In this section, we will talk about complex numbers, a new type of number here. So when we're working with radicals, we run into some problems when we're trying to take the even root of a negative number. Okay, so we need to develop a way to work around this situation. So we've got something called the imaginary number. All right, so here's our situation. If we have x squared equals 9, we can solve that. We can square root both sides, right? So let's square root x equals 3. Now, is there another number that works? Because 3 squared equals 9, so x could be 3. But what if x was negative 3? Would that also work? In this case, we've got to watch out. Yes, negative 3 also works. So for this little equation, there's actually two numbers. All right, what about decimals? Well, if we square roots, yeah, we can get decimal. This is actually going to come out to be 2.5. So x can be 2.5 or negative 2.5. Okay, so that's another possibility. Can we square root 2? Yes, we can. And we know that it comes out to be the square root of 2, or 1.414. And we can have the positive version or the negative version. Here's one little way we write that. We can write that with a plus and a minus. Sometimes we put that there. That means it could be positive square root of 2 or negative. But could we solve this? The square root of both sides. Well, can we square root negative 1? No, there is not a number. So we're kind of stuck. And so what we've done, what mathematicians have kind of done is said, well, we need something that works here. We need a number that makes this true. So let's just say that this square root of negative 1 is a number that we don't really know, and let's just call it I. We'll call it our imaginary unit. And that is what we will define I as. So now, when we square root a negative number or a negative 1, we can move forward. Okay? So these all have a real answer except for this one over here, this D. So we define a new number that we'll call the imaginary unit, which is the square root of 1. All right, so I is the square root of 1. Or if we square both sides there, then we get I squared equals negative 1. Okay? So what does that do for us? Well, let's say we want to simplify the square root of negative 36. Well, we have a radical product rule that says we can break this into two radicals. So what is the square root of negative 1? Well, that is I, as we just defined up here. What's the square root of 36? That's 6. So our answer is 6I, we say. So now we can square root negative 36, but we just have this I, this imaginary unit, and that's what we get. What if we have like the square root of negative 5? We can't really do much with that. And with real numbers, we're kind of stuck. So we can say this. We could say this is the square root of negative 1 times the square root of 5. And the square root of negative 1 we just defined as I. So we'll say that this is I times the square root of 5, or I squared of 5. That's the idea. So that one we could only take out the I there. Here we have the square root of, we might pull out negative 4 and 5. And now, all right, we can see that, all right, we could go and break this up into square root of 1 and 4, but we'll just go ahead and say this is 2I. Square root of 4 is 2. Because it's negative, it's going to be 2I. That's the idea. And the square root of 5 just hangs out. So that's 2I squared root of 5. All right, so now we can take the square root of negative numbers in that way. So this opens up the world of a new type of number, that we call the complex numbers. So we have numbers that we've talked about called rational numbers. Okay, so rational numbers are numbers like 1 and 2 and 0 and -1 and -3 and all of our decimals, 0.75, fractions, 2/3, and so on and so forth. All right? These are all rational numbers. Irrational numbers we've been introduced to. All right? Irrational numbers. Okay? And so those are numbers like, let's say, square root of 2, square root of 3. These are decimals that don't end and don't repeat. Pi is an irrational number. So we have a lot of different numbers, a lot of different square roots, and then some other unique ones like pi. Okay? And those don't mix. So in the world of numbers, we have rational numbers. And in the world of rational numbers, or their kind of next door neighbor, we might say, are irrationals. Okay? And we take all the numbers that are either rational or irrational and we put them together. Those make the reals. So altogether, those are the real numbers. All right? However, there's some numbers that are not real numbers. There's numbers like the square root of -1 or the square root of -5 that we just saw. Numbers like that. Anything that becomes an I, so anything like a 2i. All right? So these are what we call imaginary numbers. So this would be the world of imaginaries. All right? So real numbers are just the rational and irrational, and then another group of numbers are the imaginaries. Okay? So we'll say that group contains all of our imaginary numbers. Now, we have some numbers that are real, which is broken into rational and irrational. Some numbers that are imaginary, which have i's or square root of -1s that become i's. And then we can take these numbers and we can combine them into what we call a complex number. So a complex number has two parts. It's got a real part, which is this a, and it's got an imaginary part, and they're added together. Okay? So we can have a number like 3 plus 2i. And so this 3 is just a regular old 3 that we've seen before. This 2i is an imaginary part. And we can glue them together and we can make complex numbers. All right? So we have some numbers that are purely real, some numbers that are purely imaginary, and some numbers like 3 plus 2i that are a combination. Okay? And so, or 4 plus I times the square root of 3 or whatever. All right? So our little world of numbers is growing here to include all of these. Okay? And so all of these live inside the world of complex numbers. Okay? So we can have, in the world of complex numbers, we can have some that have a real part and an imaginary part, or we can have numbers that are just imaginary or numbers that are just real. All right? So complex is kind of the biggest world of numbers that you'll probably ever deal with. All right? So these are what we call complex numbers. Okay? That can be either real, imaginary, or have both parts. So let's see how we work with complex numbers. So we can add or subtract complex numbers. Now, it really turns out to be pretty simple because when we add or subtract complex numbers, we must combine like terms. All right? So even if you didn't know anything about what this I meant, anything about this square root of -1, If you are asked to simplify this, you would probably just say, well, 3 plus 2i plus 4 plus I. Let's combine like terms. 3 plus 4 is 7. 2i plus I is 3i. And that's exactly right. That's all there is to it. When we subtract, we've got to be a little careful here. So we've got to, just like with variables, okay, we've got to kind of distribute that. There's nothing in front over here to distribute, so we'll just erase those parentheses. And this becomes negative times negative 2, which would be like a plus 2. And a minus times a minus 9 becomes a positive 9i. Subtracting negative is like adding. That's what's going on. So we have negative 3 and positive 2. That's negative 1. Positive 4 and positive 9i. That is 13i. So we just combine like terms just like we would with a variable. Okay? Now multiplying and dividing gets a little more interesting. So when we're multiplying or dividing, the key is this. The key is to remember that I squared, since I is the square root of negative 1, I squared is negative 1. That's the key there. So we're going to run into that. Here we'll see. So here, again, just treat it like a variable. Treat I like a variable. Let's distribute. 3 times 4 is 12. 3 times I is 3i. 2i and times 4, again, just like it's a variable, that would be 8i. 2 times 4 is 8. And then 2 times I is 2i. Ooh, squared. I times I is I squared. So 2i times I, we get I times I, and that gives us I squared. Now, let's keep going here. These are simplifying. We can combine those because they're like terms. That's 11i. And as we just said, I squared is negative 1. So we can change this negative, or this I squared to a negative 1. See that? Okay, so we're going to change that to negative 1, which just makes this 12, and that's a negative 2. So we have minus 2. And a little more simplifying, we get 10 plus 11i. So treating it like a variable, we get that I squared, but then we swap out that I squared for a negative 1, and we go a little bit further to get another complex number. It has a real part and an imaginary part. See that? Okay, let's try one more with some negatives in it. So we've got, again, let's just distribute the negative 3 times the 4, negative 12. The negative 3 times the negative 6i, that's an 18i. Positive 2 times 4, that'd be 8i. And then positive 2 times negative 6, that'd be negative 12i. Squared. I keep forgetting that squared, watch out. 2i and 6i, 2 times 6, or negative 6. And I times I is I squared. All right. Combine like terms there. Negative 12, and this will be 26i. Since this I squared is negative 1, we have negative 12 times negative 1. That's going to be a positive 12. Okay, so we did negative 12 times negative 1, and that becomes this positive 12. And then, oh, look what happens. We've got negative 12 and positive 12. That goes away. So we end up with a purely imaginary answer. So it's a complex number, but it just has an imaginary part. All right? Now we've got a special case here. So we had one answer, one example that had a complex number. One was purely imaginary. Let's see what happens here. 3 plus 2i times 3 minus 2i. So we've got the 3's times 3. That's 9. Negative 6i plus 6i. And then minus 4i squared. Well, what happens to the middle? They go away, right? They're 0. Opposites, negative 6i plus 6i. And then we have this negative 4i squared. Well, that's going to be negative 4 times negative 1. That's a positive 4. And in the end, that's 13. So this turns out to be real handy when we multiply conjugates. Remember, these are called conjugates because one has a plus, one has a minus. When we multiply conjugates, the i's go away, and we're left with a real number, 13. Okay? That's going to be really useful in just a minute. All right, one more situation here. This seems like we should go ahead and be able to write this as just the square root of 35, but there's a little twist. We can't. We first have to pull out the i's. All right, so this is I times the square root of 5, and this is I times the square root of 7. And now this is all multiply here. And now we can multiply the i's together. That's I squared. And then square root of 5 times the square root of 7 is the square root of 35. And we see what happens is we end up with I squared is negative 1 times the square root of 35. Or negative square root of 35. That's it. So we see that when we multiply those conjugates, some very useful things happen. So the conjugate of a plus bi is a minus bi. And we saw that with radicals. And since I really is a radical, it's a square root of negative 1, the same kind of thing applies here. So let's see what happens when we multiply these conjugates. We get 5 times 5. That's 25. 5 times positive 2i, that's positive 10i. Negative 2 times 5, that'd be negative 10i. And then negative 2i times positive 2i, that would be negative 4i times I is I squared. So we have our 25, and these middle ones cancel. That's nice. And then we're left with negative 4i squared, which I squared is negative 1. So this is negative 1 times negative 4, which makes positive 4. And we end up with 29. So, again, the i's disappear when we multiply by conjugates. That's kind of nice. And so let's generalize it here. A times a is a squared. A times bi, negative bi that is, negative bi, positive bi, and then negative b squared, I squared. And that leaves us with a squared. The middle ones cancel. And we have, here we have negative 1, because I squared is negative 1, times negative b squared. Negative 1 times negative b squared would be positive b squared. And so that leaves us with the rule a plus bi times a minus bi is always going to be a squared plus b squared. All that means is we don't need to go through the steps we just did. We're not going to need to do this every time. If we recognize that we're multiplying conjugates, we'll have the first thing squared plus the second thing squared. So when we multiply complex conjugates, all right, so that's our complex conjugate. Now again, this is for complex numbers only because we have the i's. So a plus bi times a minus bi is going to be a squared plus b squared. That's an important rule there to remember. All right. So when we're dividing complex numbers, this will be very useful to us. The key here is we want to make the denominator real. Remember when we did rationalizing the denominator a couple lessons ago? Well, now we want to make the denominator real. We don't want any i's in the denominator. So the way we're going to do that is we're going to multiply by the conjugate. So the key step here is to multiply by the conjugate, the complex conjugate, that is. So we're going to multiply top and bottom by the complex conjugate. That makes the i's go away. So we want to simplify. We want to divide and simplify. All right. Well, the key is, again, we want to get rid of the I. So we got 4 minus 3i. We don't want i's on the bottom. So that's the key. So we're going to multiply by the conjugate. 4 plus 3i. All right. And now we have this rule. I'll write it down again. A plus bi times a minus bi equals a squared plus b squared. Well, what's in the a spot here? 4 is in the a spot, right? So 4 is in the a spot, so we're going to get 4 squared, which is going to be 16, of course. What's in the b spot? Well, the 3 is in that b spot. See, bi, bi. Well, b is 3. So we're going to have plus, y plus, because that's what we've discovered in our little rule here, plus b squared, so 3 squared. Now the top I'm going to have to multiply out. All right, we want to multiply this one out. So we've got 6 times 4, 24. 6 times 3i, 18i. 2 times 4, actually 2i times 4. And that'd be 8i. And then the last ones gives us 6i squared. All right. Rolling along here. So the bottom's just going to be 16 plus 9. Top, we've got, this is going to be 26i, so we got 24 plus 26i. And then 6i squared is going to be negative 6, because the I squared is negative 1. Okay, which brings us to 24 minus 6. That's going to be 18. 18 plus 26i all over, looks like 25. Now, we're almost there, but we want to write this, we want to write it in the form a plus bi. Okay, we want to separate this into 2 parts. So in other words, we want to divide by 25, but which one gets divided by 25? Just the 18? Or just the 26? Or both? And the answer is both. We've got to divide both of these. That 25 divides both terms on top. It divides the 18 by 25, and it divides the 26i by 25. All right? And then, last but not least, we can simplify if we can. 18/25 cannot be simplified, so leave it alone. We can't simplify this, so we're going to leave it alone, but we're going to write it a little differently. This is the same as 26/25 times I. Okay? If it helps to understand why, this is like I over 1, and if you multiply those things, you're going to get 26i over 25. All right, but we wanted to have it as a plus bi like this. All right, that's our final answer, and this would be our a plus b is 26/25 I. And that's how we divide. All right. And what if we have just a 5i? Well, you can think of this as 0 plus 5i if you'd like. And so we're going to multiply by the conjugate here. And so this would be 0 minus 5i, or just minus 5i. Negative 5i. Okay, but we do need, well, okay, we could get away without the negative, okay? We could have just done a positive 5i in this case. That'd be fine too. All right, and we don't necessarily need that 0. It's just negative 5i. Let's go and go with the negative, see what happens here. All right, so on the bottom, we get negative 5i times negative 5i. That's going to be negative 25i squared. Up top, we got to distribute that. So we have negative 5i times 3i. That's going to be negative 15i squared. And then that's going to give us a positive 20i. All right, the I squareds are negative 1, so this will be positive 15, 20i. And on the bottom, it'll be negative 25 times negative 1, which is 25. And last step, divide both ways here. Divide the 20 by 25 and the 15 by 25. So 15 25ths and 20 divided by 25. And then the I is going to hang out here. And that can be simplified. So let's go ahead and do that. 5 goes into both, 3/5. 5 goes into both, 4/5. And there's our answer in standard form. We call the standard form A plus BI, standard form of a complex number. All right? So that's dividing. So we can multiply, we can divide, and adding and subtracting with complex numbers. All right? One last little thing that is useful and interesting. All right? Remember, all right, so we want to write these in terms of I. So watch what happens here. I to the first is just I. I squared is, what do we say? That was the square root of negative 1 squared. That is worth negative 1, right? I to the third power, well, this is like I squared times I to the first, right? And I squared is just negative 1. So this is negative 1i, or negative I. All right. I to the fourth, what does that mean? Well, that's kind of like I squared times I squared, right? Because we add the exponents there. And so that's just negative 1 times negative 1, which is 1. Okay, so we got I, negative 1, negative I, and 1. Well, let's keep going, and we're going to see a pattern here. I to the fifth, well, what's another way to write that? How about we write that as I to the fourth times I to the first? Well, what is I to the fourth? I to the fourth is just 1. So this is just 1i. See that? I to the sixth, well, we could write that as I to the fourth times I to the second, right? 2 plus 4 is 6. So this is the same as I to the second. And what was I to the second? Well, it's over here. It's negative 1. So that's just negative 1. See what's going on here? So since I to the fourth is 1, we can break this up. 4 plus 3 is 7. So this is 1 times I to the third. Well, it's just I to the third, which we already found. Over here is negative 1, or negative I, sorry. And then last but not least, I to the fourth times I to the fourth. Well, that's just 1 times 1, which is 1. And we see a pattern. I, negative 1, negative I, and 1. And so I, negative 1, negative I, and 1. So since I to the fourth is 1, there's several ways to go about this, but probably the easiest way is just to express a given power in terms of I squared or I to the fourth, all right? I don't know what that negative is doing there. That negative's an accident there. Sorry. Or I to the fourth, okay? And then if it replace I squared with negative 1 or I to the fourth with 1. All right, so either way is a good way to go there, okay? So here we can say this. Well, this is, let's use the, whoops, go away. So this is I squared to the seventh, right? And what's that worth? Well, that's just negative 1 to the seventh. And negative 1 to the seventh is negative 1. So I to the 14th is just worth negative 1. Okay. I to the 25th, well, that is, we're going to have to write it as I to the 24th times I. Why? Because I to the 24th is I squared to the 12th, right? Why do we care about that? Well, I squared, we know it becomes a real number, -1. And -1 to the 12th, because it's an even power, is just 1. So we're going to have 1I, or just I. Okay? You just write that as I. So I to the 25th becomes I. So this makes it really nice, because it doesn't matter how big it is. This is like I to the 50th times I to the 1st. I to the 50th is going to be I squared to the 25th. Because 2 times 25 is 50. And that's going to be -1 to the 25th. And is that a positive or a negative? Well, that's going to be a -1, because there's an odd number of i's. So it's going to be -1I, or -I. All right, so that's the idea with powers. So very good. We'll leave it at that. And that's the big idea of using complex numbers when we get into quadratic functions. These will show up often. So it's useful now, because we're not stuck with the square root of -1. We can continue on and do lots more with complex numbers.